An AC servo motor takes the smooth three-phase stator control of an AC asynchronous induction motor and a permanent magnet rotor from a brushless DC synchronous motor to create a high-performance motor that's ideal for smooth, accurate, and precise positioning with excellent torque and speed characteristics. But how does it actually work? Let's take a look. On this rotor from an older servo motor, the magnets are potted in some kind of plastic. If I hold this magnetic paper up to it, yep, we see the magnets. And it looks like there's 8 of them. Here's a disassembled Sure Servo 2 motor. On the rotor, we can actually see the permanent magnets attached to the shaft under this webbing. Using webbing instead of all that plastic helps keep the inertia low, which makes the motor more responsive. And of course, we can also see the magnets using the magnetic paper. And it looks like there's 10 of them on the shaft. More magnets equals smoother operation. Another reason the Sure Servo 2 system performs so well. It's important to understand that the polarities flip with each magnet. I have a small neodymium magnet on the end of this aluminum rod. It's attracted to this guy, and then it skips over one and goes directly to the next. Why is that? Well, if this is our rectangular magnet on the rotor, the magnetic field radiates out like this and wraps around to the backside of the magnet. We can see that if I put a rectangular magnet under this dish and drop some ferrofluid on it. All the little spikes are showing us the directionality of the magnetic flux coming off the magnet, and a number of spikes shows the intensity. If I pull the magnet away, the spikes become more distributed or less intense. Bring the magnet close, and the spikes get more intense. If I flip the magnet 90 degrees, we can see the flux wrapping around to the other side of the magnet. This magnetic flux wrapping around the magnet is big because the rectangular magnets are thick. The magnets on the rotor need to be thin to keep the rotor inertia as low as possible, which means this magnetic flux will be real thin too. If I hold a thin magnet up to the ferrofluid, yep, we see a much smaller amount of magnetic flux. So the magnets on the rotor are in this orientation, which has the flux lines going out in all directions. And that explains why the magnets on the rotor alternate. I have these 2 rectangular magnets with a spacer between them to simulate the space between the magnets on the rotor. Watch what happens when I place those under some ferrofluid. Bingo! We get an enormous magnetic field between the 2 magnets. Again, instead of little spikes, we're seeing the spikes connect and go from one magnet to the next. So it's really the magnetic flux between the 2 magnets that the stator will be moving around, not the magnets themselves. If we put the rotor under some ferrofluid, yep, we can actually see the magnetic flux between the magnets rotating around. Now I can't rotate it smoothly because the magnets are grabbing and holding on to the ferrofluid. How cool is it that we can actually see the magnetic fields rotating with the rotor? By the way, this is the ferrofluid I'm using. There's lots of YouTube videos showing how to make your own ferrofluid using printer toner or powdered ferrous oxide and oil, but I've tried all of them, and none of them work as well as the real thing. This is not an Automation Direct product, so please don't call tech support asking about it. They couldn't talk about it if they wanted to. It's really fun to play with, especially with big magnets, but it's incredibly messy, so please be careful. Okay, that worked really well on the rotor. Can we do the same thing with the stator? Sure, but before we do that, we need to understand how the stator is configured. This is the stator that was around the rotor we were just playing with. It has the 3 UVW wires plus chassis ground coming out. It's wired like this. The drive's whole purpose in life is to adjust the currents in these 3 windings to create just the right magnetic field in a stator. And of course, this has to be a zero-sum game. That is, if the drive forces 3/4 of an amp in here and another 1/4 amp in here, it better take 1 amp out here. The 3 of these always have to sum to 0. Now the magic happens in how those are wound around the stator. Notice that the stator has 12 poles to wrap wire around. It's hard to see here because it's all sealed, but that looks like this, where the wires get wrapped around these guys. But why are there 12 of these? Seems like there should only be 6, a north and a south pole for each wire. Well, remember on the rotor how it was the side-by-side magnets that created the big magnetic field for us? The stator uses the same trick. If one pole is wound in a clockwise direction using the U wire, the one next to it is wound counterclockwise with the same wire to create that coupling of the magnetic fields. That gives us that side-by-side magnetic effect. Let's label this pole U and U bar, and this one little u and little u bar, indicating it's reverse wound. Likewise, V and W are done the same way. So now we'll get a strong magnetic flux between each of these poles on the stator. And by injecting more or less current in each winding, the drive can very accurately control the amount of magnetic flux between all these poles. So for example, what we would expect to see is a really strong flux here, smaller here, and the inverse of that on the other side to create a super strong magnetic field to position the rotor. Let's see if the stator's magnetic field can be viewed using our ferrofluid trick. I added these lines to show where the gap is between each of the stator windings. I'll drop a spacer in here to hold this 3D printed plastic cup at the right level, and we'll put some ferrofluid in the cup. This rotor with the encoder attached is plugged into the encoder port of the Sure Servo 2 drive, and this stator is plugged into the motor UVW port on the drive. And if you're thinking this is going to confuse the drive, yeah, the drive is not going to understand what's going on. It expects to apply a certain amount of current into the stator and get a specific response from the encoder reacting to that. When it doesn't see it, it's not going to be a happy camper. So we're going to have to fake it out. To do that, we're going to watch several things using the Sure Servo 2 Pro software that you can download from AutomationDirect.com for free. I did a factory reset on the drive, connected to the drive, and read the drive's parameters into the workspace. Here we have the scope monitoring the motor current, and I've adjusted the scale to around plus or minus 3 amps. We also have the jog dialog where we can tell the drive to enable the servo and tell it to move the rotor position. I have that set to jog at 2 RPM so things don't change too rapidly. We also have the alarm dialog in case we need to reset any faults when we confuse the drive. And we'll want to see the stator and the rotor. Here we go. Run the scope, enable the servo, and nothing. The ferrofluid didn't do anything. What happened? Well, when you first power up the drive, it assumes that wherever the rotor is where you want it to be, so it doesn't do anything. We can see the total motor current is 0 right now. If I tell the drive to move the rotor by pressing the jog button, then look what happens. The total motor current increases, and the drive builds up a magnetic field in the stator to try and move the rotor, which isn't actually there. And where is the magnetic field? Between the 2 windings, just like we saw with the rotor magnets. And look at the shape of the magnetic field. It looks kind of sinusoidal, with the opposite pole mirroring the other one. Exactly what we expect to see. Now the magnetic field is staying there because there's no rotor in the stator to react to the magnetic fields and move the encoder. The drive is going to keep pushing until it gets what it wants or it faults out. If I press jog to increase the current even more, then eventually the drive faults out. The current drops to 0 and the magnetic fields go away. And the drive gave us an overcurrent fault. Okay, let's reset the fault and jog a bit to reestablish the magnetic field. If I gently rotate the rotor, really the encoder, in the direction the drive wants it to go, it's really touchy, so I'll finish it off by jogging to 0 amps, we see the current reduce and the magnetic fields drop. Perfect. If I jog in the other direction, we get the same magnetic fields, but opposite polarity to move the rotor in the other direction. It's a shame we can't see the direction of the fields with the ferrofluid. And I'll rotate the rotor in that direction to bring it back towards 0 current, and I'll finish by jogging to a positive current. Okay, now I'm going to attempt to hold the jog button down and rotate the rotor at the same time to simulate what the drive would normally be doing. As I do that, you can actually see the stator magnetic fields rotating around. How cool is that? And that's the beauty of the 3-phase AC input to the stator. The drive can smoothly move the rotor to any position simply by adjusting the currents at each of the 3 phases to create whatever magnetic flux it needs here on the stator to move the rotor wherever it wants. We call that synchronous because the rotor is always going to follow the stator's magnetic flux exactly, unlike the asynchronous AC induction motors where the rotor always lags the stator flux. Now I say it simply adjusts the currents, but realize that requires a phenomenal amount of processing. Basically, all the stuff in the current loop block. And all of that is helped by the high bandwidth and extreme resolution of the Sure Servo 2 system. All of which explains why the Sure Servo 2 system works so well. Hopefully this gives you a little better understanding of how an AC servo motor works and why AC synchronous motors are what you need when creating a fast, accurate, and precise positioning system. and you'll have a tough time finding a servo system that can beat the Sure Servo 2 system's price and performance. From AutomationDirect.com. Click here to see all of the Sure Servo 2 tutorial videos. Click here to subscribe to our YouTube channel so you'll be notified when we publish new videos like this, and click here to learn about Automation Direct's free award-winning support options.